Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about energy analysis. First, let us understand what is the purpose of energy analysis and how this can be done by use of Aspen Plus. Now, one thing we all know that energy is an important factor in any process industries, because in process industry or in process plant, we commonly come across the equipment like heaters, coolers, heat exchangers. Now, suppose a process stream that needs to be heated, then we use a heater which eventually makes the stream hot. On the other hand, if we have a stream which is otherwise hot and needs to be cooled, then we use a cooler and that makes the stream cold. Okay. Now, a process engineer hates to throw away the heat through the cooler because heat costs money. We have to use some kind of fuel, either coal or electricity or oil, in order to produce heat. And there is no point in throwing away the heat just like that. So it is customary to use some kind of heat exchanger, whereby the heat exchanger will be placed somewhere here, where the hot stream will pass through the heat exchanger before it goes to the cooler, and the cold stream will pass through the same heat exchanger before it is placed to the heater. So in the heat exchanger, the heat exchange between the process streams, that hot stream and cold stream, they take place, and the process streams becomes preheated or pre-cooled before they are placed to the respective heaters or coolers. That way, the heat load or the heat duty on the heater becomes much less, or the running cost of the plant becomes quite less. So that's a common thing that we come across any process plant, and we are aware of such things. Now, for a couple of process stream, it is very easy to understand. But the problem comes when the process plant has multiple of such streams, which is a reality for any modern day process plant. We have multiple and huge number of process streams. Okay, they are either needed to be cooled or they are needed to be heated. Now, the common question that comes in our mind, as we have this network of process streams and they go through those heat exchangers, whether the heat exchange is happening in an optimal manner. In other words, through this heat exchanger network, as we call it that way, whether we are able to capture or recover the maximum amount of heat that is possible to exchange. In other words, whether we are unnecessarily throwing away any heat that could otherwise be recovered. Okay, so that is the question that we have to find an answer, and Aspen Plus helps us in doing that. Okay. So in order to learn this energy analysis better, we will take up a problem, example problem directly, and try to find the answer in what way we can do it better. Now, this is an example problem, as I said. The example problem says a hydrocarbon fraction containing mainly N-heptane is dehydrogenated to produce toluene and hydrogen. So the equation is given over here. Here the N-heptane is converted into toluene and hydrogen. And the conversion of N-heptane is 50%. That means whatever N-heptane is being supplied, only 50% of that N-heptane is being converted, and rest of the 50% is just going out of the system. Anyway, let us see whether we are recycling or we are doing anything with that. Let us see. The dehydrogenation process takes place at 420 degrees centigrade, is a high very high temperature, and 120 kilopascal pressure. Assume the feed, that means pure N-heptane, the flow rate, temperature and pressure has been given. It enters a reactor at 220 degrees centigrade. So it is preheated to 220 degrees centigrade before it is entering into the dehydrogenation reaction via an isobaric heater. That means at heater the pressure is constant and it is preheated to 220 degrees centigrade. The dehydrogenation process is strongly endothermic, and the reactor, the model is given Arstoic model. You know in Aspen Plus what is Arstoic model, is fire heated. As I said that there are many ways that we can produce heat. Fire heated is one of them, to hold its temperature at 427 degrees centigrade. And the reaction products are cooled to 25 degrees centigrade with 70% vapor and flushed where the hydrogen is separated. So first it is flushed and hydrogen is separated. So what is left over is mainly heptane and toluene rather. Okay. So that's what it is. Flash liquid is then pumped back to 1.4 bar and heated to 93 degrees centigrade before sending to an extractive distillation column where N-heptane and toluene are separated using N-methyl-2-pyrrolidone, that is NMP, as solvent, whose temperature, pressure and flow rate has been given. So we are sending it to the extractive distillation column where NMP is used to extract the N-heptane. Now we continue the example over here. Actually, there are two columns. The first column is extractive distillation column, which is a Radfrac column with partial vapor liquid condenser. Okay, so some vapor will also be there in the condenser and liquid outlet will also be there. It has 22 theoretical stages, including reboiler and condenser. Feed enters the column on 17th stage, NMP on the 5th stage. Condenser operates at 94 degrees centigrade atmospheric pressure. The distillate rate and reflux ratio should be set so that N-heptane recovery and purity are higher than 99%. So the distillate rate is clubbed with recovery, reflux ratio is clubbed with purity. So we have to tweak around the number. Probably we have to use some design spec. Initial guess of distillate rate and reflux ratio has been given. It is 40 kilomole per hour and 3 respectively. Now we come to the next column because we are using NMP, so NMP has to be regenerated. So NMP regeneration column has 12 theoretical stages and a total condenser which works at atmospheric pressure. Feed enters the 6th stage. The distillate rate reflux ratio should be set so that NMP recovery and purity is above 99.8%. So here also the distillate rate is clubbed with recovery rate and reflux ratio is clubbed with purity. And we have to use some design spec in order to achieve that. Initial guess of distillate rate and reflux ratio the same as that has been given in the first column. Continue the example. Assume that methane is combusted to cover the heat requirement. As it is an endothermic process, so we have to supply the heat to some extent. So it is combusted, methane is combusted to cover the heat requirement, and combustion reaction is given over here. Another Arstoic reactor operates at atmospheric pressure and heat duty. 1 megawatt of heat is being taken out of that combustion reactor in order to feed in various heater. Okay. Now air, whose composition has been given, is available at this temperature and pressure because we need oxygen, right? So air is supplied. Flow rate of air should be 10 times that of methane in order to ensure 100% conversion of methane. So we do not want any unreacted or uncombusted methane left over there. So we are giving excess air into the system. The methane flow rate should be such that the outlet temperature of the flue gas is cooled to 550 degrees centigrade. Although 550 degrees centigrade is a bit higher in the range for a flue gas temperature, but still, let us take with that example. An initial gas of 80 kilomole per hour may be adopted. You have to use Peng-Robinson method for that. Now comes the tasks. Watch what you need to do over here. So first thing is calculate the amount of methane required without any process heat integration. So the first thing, do not do any process heat integration. Perform the problem run and find out what is the amount of methane required. And second thing, how much methane can be saved if the heat of reaction and heat of flue gases are recovered. That means some sort of process heat integration is suggested over here. And for heat recovery from the flue gas, assume that they are vented to the atmosphere at 150 degrees centigrade. And finally, design a possible scheme for process heat recovery. Okay. So this is the total example problem. Now let us solve this problem and learn how to do the heat integration. So let us first open the Aspen Plus. Okay. So this is the simulation window for Aspen Plus. First of all, let us identify the components. So what are the components we have? We have N-heptane. So let us write N-heptane, or heptane will do. Yeah, N-heptane, then toluene and hydrogen. What else? We have N-methyl 2-pyrrolidone or NMP. So we have to find it. Yeah, here it is. We'll rename it to NMP. That will be easier. Okay. Then the next one. Here we do not have anything else. Here we have methane, oxygen, carbon dioxide, water, and nitrogen. Anything else? Okay, we have none. So we have these 9 components over here, and we have to use the Peng-Robinson property method. So we can use the Peng-Robinson property method. So we just keep on clicking them. I don't think anything is over there. So run it. Okay. The property method has been run. Now we have to go to the simulation window. Okay. So first thing first, we have to have a heater that will take the feed and preheat to 220 degrees centigrade. So what we can do, we can take a heater from here. So this is a heater. And then we have a reactor. So this is a stoichiometric reactor. And then we have a cooler. So first let us work with these three. Okay, so let us first name them. We will name it as heater 1. This is reactor 1. And this is cooler 1. Okay, so this is reactor 1, this is cooler 1, this is heater 1, and we will connect the lines like this. Okay, now this is feed. Let us write react in, or react 1 in. This is react 1 out. Okay, and this is cooler 1 out. Cool 1 out. Okay, so let us first simulate this part before going to the flash and other things. So the streams, only one stream needs to be fixed, that is the feed, and feed is pure heptane 25 degrees centigrade 1.4 bar. So it is 25 1.4 and pure heptane 100. So this is 100. Okay, and then the heater is isobaric heater. So the temperature is 220 degrees centigrade. Okay, so 220 degrees centigrade and pressure isobaric, no change in temperature. The reactor operates at 427 degrees centigrade and then 120 kilopascal. So it is 120 kilopascal. So it should be somewhere here. Yeah. And at this temperature, it will not be vapor liquid. It should be vapor only. So remember that. Go to the reactions. In the reactions, you have to enter this particular thing, C7H16. So it is heptane converts, one heptane converts into 1 toluene and 4 hydrogen. So it will be 1 toluene and 4 hydrogen. Okay. And fractional conversion, it is 50%. So we write 0.4 of heptane. So that way we set the reactor and now the cooler. So cooler temperature is 25 degrees centigrade and 70% vapor. So it is 25 degrees centigrade and vapor fraction is 0.7. Okay, so that way we have set it now. Assume 100 kilomole per feed. So the feed is entering the reactor via an isobaric heater, and the dehydrogenation process takes place over here, and the reaction products are cooled to 25 degrees centigrade. So let us run it once and check the temperature. And yeah, so this is the feed temperature 25, entering the reactor at 220 degrees centigrade, and it is coming at 427 degree. Okay, and cool out to 25 degrees centigrade. Okay. And if we check the pressure or vapor fraction, it is 0.7. Okay. If you see molar flow rate, okay, let us not use pressure over here. Vapor fraction is okay. But for the time being, temperature is only okay. Now, next part, the reaction products are flashed where hydrogen is separated, and flash liquid is then pumped back to 1.4 bar and heated to 93 degrees centigrade before sending to an extractive distillation column. So we need a flash tank, a pump, and a heater, all in series. So let us take a flash tank first. So we have a flash tank, then a pump, and finally a heater. Okay, so we will connect them accordingly. So connect to this one, then connect. This is the hydrogen is separated. So this is the hydrogen line, and the flash liquid is pumped back to 1.4 bar. This is going to a cooler. Okay. So open the flash. Now, nothing is said about the flash. What temperature, what pressure. So we will assume the pressure is constant. Okay, there is no pressure change and there is no heat duty. So it is just a separation of vapor and liquid. That's all. So we will use no pressure drop and no duty. So both of them we will take 0 and 0. That way we define the flash. Okay. So flash is used only to separate the vapor and liquid in whatever the condition it is. So here we find it is 70% vapor. So let it be 70%. All the vapor goes through S5. And we will call it hydrogen because hydrogen is escaped over here. Some amount of other things will also be there that we will check later. What other thing other than hydrogen will be there. Some NF10 will be there. Very little amount of NF10 or some other things. Let us see. And this is flash liquid, which is pumped back. So this is a flash tank. So we just write over here flash, and this is pump. And this one is cooler. Cooler 2. Okay. And pump, the discharge pressure is 1.4 bar, right? So it is 1.4 bar. And it is heated to 93 degrees centigrade. So, okay, so it is not a cooler, it is a heater, right? So it is a heater 2. So it is 93 degrees centigrade. And there is no pressure drop at all. Because whenever nothing is said about the pressure, we will assume there is no pressure drop at all. So we call it 0. Delta P is 0. And we name it first. We write it as pump out. And this one will go into the extractive distillation column unit. So there are two units, distillation 1 and distillation 2. So we will name them dist 1 and dist 2. So Let us name it as dist1 in. Okay. So let us run it. Yeah. So we find the temperature over here. Okay. All of them, it comes to 93 degrees centigrade. Okay. We can do some kind of cosmetic changes so that it looks better. Okay.